Reynolds number was calculated, and based on that, say, should it be either terminal or lambda? We don't care about that. So, for right now.
Look at all that science. That's a lot of science. Yeah. Aperture laboratories and stuff.
Okay, so it's done. So now we can look at the velocity, for example, post-process, plane cut. And let's cut it in the Z direction, Z plane. And let's show the vectors. All right, so you can see,
That's science right there.
right, so if I go way up, should be 0 on the wall. Right?
Tomorrow we'll take over the world.
Very small.
What the heck is this coming?
Right, and then moving along, it should accelerate. As soon as it sees that stuff, right? And acceleration, right? Higher velocity because conservation of mass, right? And then we can see that. So now you can look at the contours.
So to solve a power itemization, we do what you did on the first problem, and you figured out how it was flowing out.
Yes. So the whole idea now is, why did you do this exercise? So typically, if you look at the wire bonded, stack packages and so on, you want to see where's the opportunity. For example, it may be possible if you have a ball grid, if you have a package, a molded package, you might be able to move the chip closer to the bottom of the molding so that you can supply a path. You can supply a viable path for the heat to go, even though the thermal conductivity is small, because the distance starts getting smaller, it might end up being a viable path. So you want to be able to look at, the device now has how many watts? 10 watts, right? There are 10 watts. So you look at different surfaces. So you go up here to report and say,
Sure.
summary report, and you create.
This is how to
So I think the thing to look at, for example, if I look at the die, heat flow, all surfaces, what would you expect this to be? If I say, right, what should this be?
It's giving out 10, right? Was the input is 10?
Yeah.
How
Should-
much should this be?
Should be giving out what it was put in.
Yeah, which is what?
What, 10?
I think it's
Is it 10,
5.
5 per die or 10 per die?
So,
Okay, it's a 5.
so there it is, 5 watts, right? And so on. Now though, this is not the interesting thing. The interesting thing is now you start looking at the molding, and you look at the top surface of the molding, the Y direction, for example. I should expect almost no heat to go, even though that's a very big surface. Let me just look at the maximum one, all right? Heat flow. Right. So you can see, there's, I don't know what I put the, so there were 10 watts altogether, right? From the 10 watts, less than 10% of it is going to the top surface, right? And in this case, the molding has a very, very high thermal conductivity relative to where it should be. And also the dimensions is not good. In general, from the top surface, very low, 10% right now is really high. Now, where is this thing going? You really should be looking at the top of the substrate. If I look at the top of the substrate,
You think you can do it?
right?
Think what?
You got it?
Right now, I
Now, if I look at the,
Yeah, I definitely have the top.
right?
But this, the heat
things
transfer
are,
coefficient, that's the wall thing, right? And there's the
Yeah.
coefficient.
That's the wall.
The
But
north
that's
space
only
is
for the
maximum
top surface of the
of the
PVC.
So
substrate.
it's exposed to air.
And if I say right,
Makes sense. So making a heat sink around it.
so you can see the majority of the heat is going through there, right? Now, what that means is, if I now look at the molding, all of the molding, and if I look at the
So this is where we
maximum
get all the
Y,
answer.
So you get all
and
the
then the
answers.
other four sides, right?
For
Let
this,
me,
we have to turn off
I'm
the
just
flow,
being
right?
lazy,
Yeah.
let me say
At
all.
the very beginning lecture.
All right, if I say all,
Then I said 8 to like 10 minutes.
and
Fortunate.
right,
I think I remember all the steps.
I have it in here.
Okay, did you reduce the power?
Yeah, a lot. There were a lot of little steps.
so maximum, so if I want to see min X, yeah, that's more like it. Now, if I keep adding, let's just add very quickly. Molding. Max X. And then we add so these are the five sides.
We can do the whole thing now. The whole thing we can do now.
Yes,
Yes.
max Z,
Yeah.
no min Y.
You have to change your value, don't you, for each of those?
What's that?
They're currently, the last
Temperature.
four are all temperature. Don't you have to change the heat flow?
Oh, yeah, thanks.
Good catch. Tricky hobbit. Taste Cheetos.
Yeah, I still got
Yeah.
it. So tempting.
So you can see that out of all of that heat, right? I don't know why I shouldn't have had min Y.
I think it's
Because
activity.
min Y is
It was.
actually,
Dr. Agenhofer?
yeah.
I think your molding, your conductivity was a lot higher than it should have been. I remember you had said something about that.
Yeah, I know, but that's not even,
Oh.
I don't think I should have, let me take out this min Y.
It's the very bottom.
So, the min X,
Where were we?
oh, I need a max Y, so now let me add a max Y.
825.
Okay, so this makes sense, right? So if I now say right, okay, this is the heat flow. So we have, out of the 10 watts,
No.
this much goes through the sides, right? The rest of it is going straight down, yes?
So, is this what we call the power itemization?
Yes. Yeah, this is what you do for the power itemization. Now, if I look at, now, if I'm now looking at the, let's look at the PCB, all right?
Ask that like right
So
now.
let's clear this and look at the PCB, and then we, class is over. So now let me look at the PCB, all right?
Quick question.
Dr. Agenhofer, quick question. What do you mean by junction temperature?
Junction temperature
Yes, sir.
is the average temperature of that surface. So, because there's really no, we're not talking about a single point. It depends on whatever you have that's gonna find the average over that.
So it's like where
The
you're,
actual junction temperature, when we say junction temperature on a die is, it's really, typically we're talking about TJ max, the max. And
That's what I thought.
because the temperature of the chip is highly non-uniform. It could be 10 to 30 degrees C across the die.
Where could we find that information? Because right now this is showing us the power itemization.
You can't, I mean, you're not gonna get that information because the die right now, how are you modeling the die? We just put power,
Right.
uniform generation. It doesn't go like that. So if you're interested in the kind of detail, you can read it some of our papers. You know,
so we can't compute
you
the
can
junction
read some of our
temperature of a
papers
chip?
that
So we
show you-
can't compute the junction temperature.
No, there's nothing like a junction temperature here. I mean, you can find the maximum temperature, right?
Interesting.
But you're applying uniform, in other words, this is not really a realistic thing. Now,
Well,
let me just show you this and then I'll
Yeah.
I'll
Which
answer
is-
that. If we look at this now, let me just see. Oops.
the reason why I asked that is because the midterm is asking us to find the junction temperature of all three chips.
Oh, so what I'd be expecting you to find, let's do that. Let's do that right now.
Thank you.
Summary report. So what it should be here, it should be, it should be,
Temperature, right?
if I look at the temperature,
All.
so the best it's gonna give you is whatever the temperature of the die is.
Okay,
Is what I'm expecting.
that's what you're expecting. Okay,
Okay,
perfect.
yes. So right here, you know, for example, if we're looking at the die, yes? So let's take at the die, right? So, yes, so that's really, I want you, this is gonna find the average temperature of the die. That's really the best you can do,
Okay.
right? In this case, it's 75 degrees C.
Thank you.
Yeah, one thing, how many of you here are undergrads? So, yeah, for those of you who are undergrads, if you're interested in the CFD class, for some reason, they didn't include that, you know, there are 40 students already signed up for the graduate class, so Lainey's gonna put that class in for next semester, if anyone is interested. So in case you couldn't find where that is, Lainey will have that, by next week. All right, so I'm gonna close this up. So we pretty much then have, you now know how to, there was a bunch of problems, and I got a lot of questions, and I think that was fair questions.
Okay.
There's always people you have to.
Well, if anything, there's always Wednesday.
Yeah.
So